Hi everyone, thank you for joining us today. I'm presenting ExCamera. This is a joint work between our team at Stanford University and George Porter's group at UC San Diego. I'm going to tell you how we used AWS Lambda as a supercomputer to do low latency video processing. Let's talk about our vision and goals for this project first. So we currently have this product called Google Docs where people can make changes to a word processing documents, and other people can see those changes in real time. But what we would like to have is a system like this, but for video, where people can edit and transform a video, and they can instantly share that video with other people. For example, you might want to apply some filter to your video, or you want to go through a movie and look for a certain face. Or maybe you want to remove Jar Jar Binks from Star Wars. The problem with all these pipelines is that currently they take hours and hours to run, even over short videos. Because there are a lot of frames in videos, there are a lot of information, and we have to process all of them. We have to go through all of these frames, and it will take a long time. So the question is that, can we achieve interactive, collaborative video editing by using massive parallelism? The answer is yes, and I'm going to tell you how. So there are two main challenges here. First of all, to do low latency video processing, we need thousands of threads with instant startup, each operating on a very small chunk of the video. So we need a way to get all these threads. Second of all, the finer grain the parallelism, the worse the compression efficiency, which means that as your chunks get smaller, your file size will be bigger. And after some point, it's even too big to store on disk, let alone transmitting over the network. So in this project, we addressed these two challenges. First of all, we built a framework to run 5,000-way parallel jobs with inter-process communication on a serverless platform, AWS Lambda. Also, we made this purely functional video codec intended for massive parallelism. We call the whole system ExCamera, and it can be used to do low-latency video processing. OK, let's talk about the first contribution. Traditionally, if you wanted to have like thousands of threads, you can use a service like EC2, Azure, or Google Cloud to provision thousands of machines, and just you can run anything you want on them. But there are two problems here. First of all, it takes minutes for each machine to start. The OS has to boot up and stuff like that. And it's bad for interactivity. Second of all, even if you want to run your code for like 30 seconds or 1 minute, in case of, for example, EC2, you still need to pay for 60 minutes. Or in case of Google Cloud, you at least need to pay for 10 minutes. For example, if you want to run 3,600 threads on EC2, each running just for 1 second, you need to pay at least $20 for the worst machine. Recently, these cloud providers, they started to offer a service called Cloud Functions, where you can just upload your code, and they will provision servers, and they will run your code for you. These services are intended for event handlers and web microservices, but we realized that there is an untapped potential here. You can actually invoke thousands of these functions in parallel, and also with some tricks, you can run arbitrary Linux executables on them. But there are two features here that were absent from the traditional approach. First of all, when you invoke a function, a few milliseconds later, it will start running. And also, if you're running your function for like half a second, 1 second, or 1 minute, you're just paying for that time. So if you want to, for example, run 3,600 threads on AWS Lambda, each for 1 second, you're just going to pay 10 cents. To harness this power, we built this library called Mu, where you can design and deploy general-purpose parallel computation on AWS Lambda. And this system can start up thousands of threads in just a few seconds, and it can handle inter-process communication. Mu is open-source software. If you were at the conference yesterday, you've probably seen this guy just walking around with a camera on his head. Actually, he's my colleague, John Emmons. And yesterday, we recorded 6 hours of video from the conference. And we uploaded this video in uncompressed format to S3. Also, John adapted OpenFace, which is an open source library for face recognition, to run on AWS Lambda. And we want to go through this long video and see if George Porter actually showed up yesterday. So we are going to run about 2,000 lambdas and just look for that face. So if you go to ExCamera, on the left side, you can actually see the actual video uploaded on YouTube. And after the demo is done, you can see the George Porter montage on the right side. OK. So we found this photo of George on the internet. I'm just going to grab the URL. And here, in the demo environment, I'm just going to download that photo. And then I will run the script demo upload face, which is going to upload that image to S3, and then it will fire up thousands of lambdas to go through that video and find all the scenes with George in them in just a few minutes. OK. It's running. We are going to go back to the demo in a few minutes. OK. Let's talk about the second contribution. Now we have a way to access all these threads in the cloud, okay? But the second problem still remains. With current encoders, with current video codecs, the finer grained the parallelism, the worse the compression efficiency. I'm going to tell you why first, and then I will talk about our solution. Video codec is a piece of software or hardware that is responsible for compressing and decompressing the video. On one side, we have the encoder that reads the uncompressed video and generates the compressed video as the output. And on the other side, there is the decoder that reads this compressed video and produces uncompressed images that can be, for example, displayed on the screen. Current video codecs, like the ones that YouTube and Netflix use, they try to exploit similarities between adjacent frames to make the video as small as possible. The way that these video codecs work is that they store the first frame in the sequence on its entirety. We call this a keyframe. It's a standalone frame. But for the other images in the sequence, instead of just storing the full image, they store a diff. They store a delta between that image and previous images. We call these interframes. In a 4K video at like 15 megabits per second, a keyframe could be around a megabyte. But an interframe that is like a delta, it could be like 40, 50 times smaller, maybe 10, 20, or 25 kilobytes. So naturally, we want to have more interframes in our video and less keyframes. This is the interface that current video codecs expose. So as you can see, there are two functions. And that's basically everything we get. We have an encode function that gets a stream of images, and as the output, it produces a compressed video, starting with a keyframe, because you can't start with a delta, right? And there is the decode function that reads in this compressed video, again starting with a keyframe, and produces some images that can be displayed on the screen. So imagine that you have a video with 200 images in it, and you want to compress that. So if you only have one thread, you want to do that serially, you pass all of those frames to the encode function. And as the output, you will get one keyframe in the beginning and 199 interframes after that. Now, if you have access to 20 threads, you can cut your video into 20 parts and just encode them separately on separate threads. So this is what you get. But as you can see here, every thread's output is starting with a keyframe. So I end up with all these extra keyframes here. And they will add, each will add like a megabyte to the size of the video. So in the serial case, I had only one keyframe, and now I ended up with 20 keyframes. This is why, as you increase the level of parallelism, you get worse compression efficiency. Why is that? The reason is that I can't start encoding midstream. I can't start encoding with an interframe. I always have to start encoding with a keyframe by using this interface that the video codecs expose. Starting encoding midstream requires us to access to the internal information of this black box. We need to see inside the encoder and decoder to be able to start encoding with an interframe. But traditional video codecs, they do not expose this information. What we did is that we took VP8 format, and we formulated this internal information, and we made it explicit. And we call it the state. So this is how the state works. So you start playing your video with a keyframe. You always have to start with a keyframe. And it doesn't need to be applied on a certain state because it's completely a standalone. So you apply the keyframe, you get an output that you can, for example, display on the screen, and the decoder will go to the next state. Now you can apply the next interframe onto this state, get the output, go to the new state, and you can decode the whole video in this fashion. What we did in our video codec is that we made that state object explicit. So you can transmit that over the network, you can save it to this, you can do anything you want with that. So we built this video codec in explicit state passing style. Of course, I have to say we did not invent a new format. We are using Google's VP8 format, but we built a video encoder with a different interface. So there is this decode function that as the input, instead of getting a bunch of frames, it gets the state object and it gets the frame. It applies the frame to the state and gives us the target state, the next state, and an image that we can process or display on the screen. Now, if you want to decode the next frame, you just grab this target state and pass that to the decode function alongside with the next frame. Also, we built this encode function that can start encoding midstream. As you can see, the encode function gets a state and an image as the input, and it produces an interframe. So basically, if you apply this interframe to the source state, you will get that image. And also, we invented a new operator called rebase. It's like rebase in Git. Imagine that 1,000 developers, they make a commit at the same time. Then you can rebase all these commits together to get a linear history. Now we have thousands of threads encoding a video separately, and we can use the rebase operator to just put all of them together to have a linearly playable video. OK. Now we have the threads. Now we have a video encoder that can start encoding midstream. Let's put it all together and see how ExCamera works. So in a parallel process, I will do the traditional thing. I will split my video into tiny chunks. And by tiny, I mean like 6 frames, 10 frames, very small chunks. And I will encode all of them in parallel. The encoding process is a slow process, but I'm doing that in parallel. What the problem is? The problem is that I will end up with all these extra keyframes. To get rid of them, in a serial process, we go through the video and we rebase these chunks together and we remove those extra keyframes. Let me show you how. So here I'm displaying like 4 threads, but it could be 4, 8, 16, any number. In the first step, each thread will download a very small chunk of the video that it wants to compress. It downloads an uncompressed chunk, and as the output, it will produce a compressed video. In the next step, I will use a traditional video codec like Google's VP8 encoder, and I will compress that chunk. As you can see, now I ended up with a keyframe at the beginning of each thread. Now I will use our own decoder to grab the final state, and each thread will pass that state to the next thread. And then I will use our encode function that can start encoding midstream to re-encode that expensive keyframe into an interframe. Now, all I have to do is that I go through this and rebase these chunks together. So I will rebase thread 3 on top of thread 2. And then I will rebase 4 on top of 3, 5 on top of 4, etc., until I get a fully playable video. There are different configurations for ExCamera. There can be different number of frames in a chunk, and there could be different number of chunks that we want to rebase together. There are more details on this in the paper. OK, let's look at the results. So we evaluated ExCamera on 1 animated and 1 live-action movie. This is the results for that animated video. This is a 15-minute-long 4K video. This is quality versus bitrate. As you can see, as the quality increases, the file size increases too. The blue line is Google's encoder running in single-threaded mode. It gives us the best compression efficiency, but it's slow. The orange line is Google's encoder now running in multi-threaded mode with maximum parallelization available, which is 32. And it's faster, but it gives us worse compression efficiency. If you do a naive thing with 6-frame chunks, this is what you get. Okay? As you can see, the compression efficiency is worse. But if you try to rebase 16 consecutive chunks together, this is what you get. This line, it's within 3% of VPX running in multi-threaded mode. The results for the live-action movie was within 10%. OK, let's look at the timing values. So if you run VPX single-threaded, it takes 7.5 hours to encode that video, to compress that video. If you run in multi-threaded with the maximum parallelization available, it takes 2.5 hours. So you are using 32 cores, but you only get 3x speed up. And if you just upload that video to YouTube, from the end of upload until the video is available, it takes about 37 minutes. But if you use ExCamera with 6-frame chunks and 16 chunks rebased together, it only takes 2.6 minutes by using around 4,000 threads in the cloud. OK, it's time to go back to the demo and see if we could find George Porter. OK, I'm just going to refresh this page. Oh, look, that's George. This is not George. OK, this is AI. I'm sorry. OK, that's George. So it produced a 30-second long video, I think, yeah, 24 seconds. And we went through a very long movie, 6 hours long. It's like 500,000 frames. And we made a 24-second video with all scenes with George Porter in it and some other people. OK, let's go back to talk. We believe that the future is granular and massively parallel. We have access to all these threads in the cloud, and we can use that for all kinds of cool applications. For example, instead of running make-J8 to compile an application with like 8 cores on your machine, maybe in the future you can run lambda make-J1000. You can use 1,000 threads in the cloud. And there are a lot of other applications that can benefit from these threads in the cloud. And you don't need to have a lot of money just to set up your own cluster or anything. You just pay for what you use. OK, ExCamera does low-latency video processing. We made 2 major contributions. First of all, we created a framework to run 5,000-way parallel jobs with inter-process communication on AWS Lambda. And also, we built a purely functional video codec that is intended for massive, fine-grained parallelism. It's 56 times faster than Google's encoder running in multi-threaded mode, and it costs less than $6. Thank you.
Hi, this is Pratik Sharma from UMass Amherst. I have a question regarding your use of lambdas, which are like originally for very short-running event handlers and not for this batch thing. And you said it takes like $6, which seems quite a lot. I mean, you can do a lot of, if you use traditional VMs or like even containers, like with Spot VMs, you can get a lot of processing done in $6.
Let me see if I understood the question correctly. So you're saying that if you're using VMs, we can actually pay less and get more?
That's my question. Like, have you compared with like normal VMs?
So as I said, for example, if you want to run 3,600 threads, that's what we ran on Lambda. So if you want to run 3,600 threads on EC2 for the worst machine with like half a gigabyte of RAM and like 1 CPU, you still need to pay like at least $20.
And what about normal video processing, like not with?
OK, in normal video processing, you can use VPX. You can use Google's encoder in multi-threaded or single-threaded mode. For example, for that multi-threaded mode, it takes 2.5 hours on a 32-core machine. Okay. And that machine is much more expensive. It could be like maybe $5, $10 per hour.
I don't think so. But anyway, we can discuss it offline.
Yeah, but yeah, sure.
Sure, thanks.
Thank you.
Marco from Kamst. So this is the most amazing presentation at NSDI so far.
Thanks
The only thing that would have topped it is if you had the guy actually stream live on your slides. So my question is regarding so if I understood correctly, you have 5,000 way parallelism when processing this. What is the assumption that you're making about the storage system and the way that the video is actually being stored? Because you might be running into a bottleneck simply by having to read from whatever the storage system is.
Thank you so much. I think that's a very good question. So currently, we are storing a big chunk of raw video in a service like S3, and Lambdas are actually connecting to those S3 servers to grab these chunks. So there is one problem here. So the video must be accessible in those small chunks. But I think other than that, we did not face any kind of problems, because each thread will download like a 50 or 100 megabyte file, which is that uncompressed chunk of the video, and as the output, it will produce a file around like 1 or 2 megabytes, which is the compressed video, and just upload that back to S3.
Okay, thank you.
Thank you.
Hello, I'm Kevin Spiteri from UMass Amherst. So in the example, you had the first thread had the first 6 frames, and the second one had frames 7 till 12. And then when you're stitching serially, you drop frame 7 and re-encode from serially. Would it work if you give the second thread frames 6 to 12, and then serially you just have to truncate the keyframe and not have to do any re-encoding at all?
Okay, thank you for your question. Actually, we cannot really do that, because basically all of the previous interframes and keyframes, they affect the state. And the thing is that if you can't just, so if you start encoding from frame 6 to 12 instead of 7 to 12, you start with a keyframe, right? And the second frame will be an interframe. But that is different actually from starting from frame 1 with a keyframe and encoding up to 7 with interframes. Because every frame, every keyframe, and every interframe in between, they will affect the state. And you need to have all of them. So because basically the interframes are not just basic deltas. They are something a little more than that I didn't get into that actually in this talk.
Thanks.
Thank you.
Okay, let's thank the speaker again.
Thank you so much.